So today we're going to be doing scalar line integrals and wire/spring questions, and there are two questions in particular which appear very often in this type of question. The first one we're going to do is a spring which has or could be a wire, has a shape that can be modelled by this parameterization. Find the length of the spring, and if we just look here, courtesy desmos.com, here is the spring here. Okay, so basically some people may be unfamiliar with this format, so I'm actually going to do it by both formats just to get people familiar. But basically all this R of t thing means is it's a vector from here, so that there is the vector where t equals 0, and this bit here, for example, is the vector when t equals something else, and the one at the end here is the vector here when t equals 4 pi. Finding the length of the spring is exactly the same as finding arc length. And we've done before in previous videos that arc length is basically the integral over the curve of 1 ds. Okay, now basically that is the same as the integral over the curve of 1 ds dt dt, and that is the same as the integral over the curve of 1 times the magnitude of the derivative of the vector r dt, and we're going to see that in a minute. But basically ds is the same thing as the magnitude of r dashed of t dt, and that's the easiest way of converting between the two different formats. So anyway, let's have a look. So here's the parameterization here. So let's just write that. So basically r of t vector is equal to the vector cos t sine t 2/3 t to the 3 over 2, and that is exactly the same thing as saying that x equals cos t, y equals sine t, and z equals 2/3 t to the 3 over 2, and then r dash t, i.e. the derivative, is equal to minus sine t cos t and t to the power of half, so 3 over 2, so that's t to the half, and that is exactly the same thing as saying dx equals minus sine t dt, dy equals cos t dt, and dz equals t to the power of half dt. It's exactly the same thing, and then basically the magnitude of r dash t is going to be equal to the square root of that squared add that squared add that squared, which is exactly the same as ds dt, which equals the square root of that squared add that squared add that squared. So they're basically just different ways of writing exactly the same thing. So anyway, let's just put it in here. So it'll be the square root of sine squared t add cos squared t add t to the half squared, which is t, sine squared add cos squared t is 1, so that's the same thing as root 1 plus t. Now all we need to do now is go back to our arc length formula, and we're going to use this one. They're all exactly the same, so it's the integral of 1 over the curve, magnitude of r dash t dt, so that gives us the integral over the curve, which was between 4 pi and 0 of 1 times by what we've just calculated here, root 1 plus t dt. This is going to be the length of the wire, which equals 2/3 1 plus t to the 3 over 2 between 4 pi and 0, and that is 2/3 1 plus 4 pi to the 3 over 2 minus 1, and that is the length of the spring. Okay, so basically that's question type number 1, and so just don't get confused with this different form in vector rather than in the more traditional parameterization form there. So that's the first one. It's basically just arc length. Now the second question that they ask is to find the density, is to find the mass given the density. So this is question number 2. Calculate the mass of a wire here is the shape parameterized by this, and they are giving us a density function. So again, it's going to be a scalar line integral. But basically this time it's going to be the integral over the curve of rho, which is the density function, x, y, z, ds, which we now know because we know that ds is the magnitude of r dash t dt, so therefore that equals the integral rho x, y, z, which we're going to convert into t form times magnitude of r dash t dt. Okay, so all we got to do now is we got our parameterization here. Basically the x bit is t, the y bit is 2 cos t, and the z bit is 2 sine t. So let's work out the magnitude of r dash t, which equals, well, first of all we got to work out the r dash t. So r dash t here, let's put it here, r dash t is going to be basically just the derivative. That'll be 1 minus 2 sine t, just differentiating these, 2 cos t, and therefore magnitude of r dash t is going to be the square root of 1 squared add minus 2 sine t squared add 2 cos t squared, which equals the square root of 1 add 4, which equals root 5. Often you will find you get sine squared add cos squared, and so therefore going on to the, here is the mass, which is the density times by ds. So here, basically going down here, we now have the mass is equal to the integral over the curve between the parameters t equals pi over 2 and t equals 0 of rho of x, y, and z. Well, now what we need to do is we need to put in our parameterization into e to the x, add y, z. So we know that x is t, so that gives us e to the t, add, well, y and z is 2 cos t and 2 sine t, so that'll be 2 cos t times 2 sine t, times by ds, which we know is the magnitude of r dash t dt, which we have already worked out. The magnitude of r dash t is root 5, so that'll be times root 5 times dt, and all we need to do now is just tidy this up. So that equals the integral t equals pi over 2 and t equals 0. We can take the root 5 out of e to the t add 4 sine t cos t, which is the same thing as 2 sine 2t dt. Integrating that gives us root 5 e to the t minus e to the t minus cos 2t between pi over 2 and 0, which is root 5 e to the pi over 2 minus 1 minus 1 minus 1, which equals root 5 e to the pi over 2 add 1. And that is the mass of our wire given the density function. So these are both scalar line integrals. They're very similar. One of them basically has the density function in, and the other one, which is just the length, just has 1, and then both are multiplied by the magnitude of r dash t dt, or if we're doing it the other way, by ds dt dt. Okay, well, I hope you found these useful. They are quite common questions, and if you can understand them, they're relatively straightforward. If you enjoyed this, please press the little thumbs up button and subscribe to the Gresty Academy YouTube channel.